Millikan oil drop experiment.
Now that Thomson had measured the charge to mass ratio of the electron, if the physicists could figure out either the charge or the mass, they would then know both quantities. His team made several attempts to measure the charge of the electron using water droplets in an electric field, and don't worry, we're going to talk about that in a few slides. Using that method, Thomson assigned a value of 1.03 times 10 to the minus 19th coulombs to the charge of the electron. As we showed earlier in the course, the charge on the electron is actually closer to 1.6 times 10 to the minus 19th coulombs. So although Thomson had the right order of magnitude, he had the 10 to the minus 19 right, the percentage error of his measurement was 54%, which is certainly not acceptable. But it was left until 1909 when a graduate student, built on many years of experimentation by many other physicists, and actually refined the method to come up with the charge on the electron in an afternoon. Then after more months of tedious experimentation, a more accurate value for the charge on the electron was found. The idea is pretty straightforward, and first we'll talk about how Thomson and others tackled the problem before this graduate student came along and just nailed the exact value. It's a pretty straightforward concept, and we've already done some work on this in the earlier chapters. An object, in this case let's take an object with charge q and mass m, will fall at a constant velocity if the sum of the forces in the y direction are equal to 0. So we have QE going up, mg going down. So basically, if QE is equal to mg, then the object will fall at a constant velocity. So why can't we just get a few electrons and measure them? Well, frankly, because they're too small to see and we don't know their mass. So what Thomson and other physicists decided to do was take water droplets and see if they could get them to float, or again move with a constant velocity with zero acceleration in an electric field. This way they can estimate the mass of each drop and then see what the charge was on each drop. By measuring a lot of drops, and this is a really huge number, this experiment could go on for days, weeks, etc., they could find the smallest charge and figure maybe that was the electron's charge. But the problem with using water is water evaporates, so the mass is going to change, so this experiment won't be perfectly accurate.
A graduate student of Robert Millikan, Harvey Fletcher, solved this in an afternoon. He bought a perfume bottle and filled it with very fine oil used for watches. Unlike water, oil will not evaporate. He then drilled holes in a couple of sheets of metal and connected a battery so that he could change the voltage to the plates. He used a microscope so he could see the drops fall. The method worked immediately.
The idea was just as the oil was sprayed, it would pick up some charge, just like the water droplets would. And actually a side benefit of using the oil, it was quite pretty. Fletcher talked about how when he first saw it, it looked like a bunch of miniature stars glowing in his apparatus there. So, if the charge is only carried by an electron, then when the charge on the oil drop was measured, it would have to be some multiple of the electron charge. You just had to find the common denominator of the charge measured on all the drops, and then the smallest one you could extend out a graph, and that would be the charge on the electron. Harvey adjusted the electric field, right here. Your electric field was several thousand volts, and he adjusted it so that these oil drops fell with a constant velocity. He estimated the size of the drop, and again he's looking at it with a microscope. Here this is a simulation of Harvey's eye. He would get the size of the drop, and then he could figure his mass because he knew the density of the oil. So now the electric field was known because it was set, and the mass of the drop was found because it was calculated from its size and also by the density of the oil. Once these data were all collected, Harvey calculated the charge on the oil drop. He did it for a large number of drops using the Below approach. We've got the electric field going up, delivering a force up, the gravity pulling it down. So we have the electric force minus mg equals 0, and we have, this is the charge now on the individual oil drops, and it's mg divided by E. And we know all these quantities. So many hours were spent by Harvey staring into the microscope watching the sparkling oil drops. What's missing in this calculation is the real-world correction. You also have a viscosity of the oil drops, and that will provide an upward frictional force. And that's going to be up like that. And using the Navier-Stokes equation, and we certainly don't need to know that in high school just yet, that would calculate what the frictional force was, that was added, and then all the data were graphed, and this was laboriously performed without the help of computers. They didn't exist then, and you now had a graph, and that would actually give you the charge on the electron. The experiment was repeated again and again with increasing accuracy by many other groups, and the accepted value of the elementary charge, or the charge on the electron, is 1.602177 times 10 to the minus 19th coulombs. And for those of you who will be taking physics in college, this is a pretty standard experiment to be done. And it is very laborious and very time consuming, and staring into the microscope for long amounts of time. Here, maybe someday this will be your eye over here looking through a microscope. It takes a lot of time, but you do get the result after you do all the work, and you'll find out the electric charge. Here's a picture of the experimental setup that was used by Robert Millikan and Harvey Fletcher to determine the charge on the electron. And it's a little tricky to see, but if you just look right here, that's a lab bench. The entire setup fit on one lab bench, and that's how they came up with the charge on the electron. The actual data were much messier than the previous problem, and the units were in 10 to the minus 19th coulombs, but the conclusion is the same. The electron was shown to have a charge of 1.6 times 10 to the minus 19th coulomb, and the mass of 9.1 times 10 to the minus 31 kilogram. And again, remember the mass of each individual oil drop was calculated by measuring its size and also knowing the density of the oil. So we now have two of the most fundamental pieces of information: charge on the electron, mass of the electron. This charge is also called the elementary charge. It is the smallest charge found in nature. So the charge on any object is always an integral multiple of 1.6 times 10 to the minus 19th coulombs. Later on in the nuclear physics chapter, we'll talk about quarks, which actually have 1/3 and 2/3 the value of the elementary charge. But they don't exist on their own. They're only in the nucleus. So we keep this statement here: the smallest charge found in nature is 1.6 times 10 to the minus 19th coulombs, and that is also the charge on the proton. Proton would be positive, the electron is negative. Hopefully you've noticed that we've been talking about Harvey Fletcher a lot here, so you may wonder why it's not called the Fletcher oil drop experiment instead of the Millikan oil drop experiment. Harvey was Millikan's graduate student, and Millikan had made very special arrangements for him to attend the University of Chicago. He didn't have the correct prerequisites to go there, but Millikan made sure he got in, then helped him the entire time he was there. Millikan had been working on the electron charge problem for a long time, but it was Fletcher's idea that galvanized the research. Millikan, as the senior person, wanted the main credit. Because of this project, he became the first American to win a Nobel Prize for physics. Harvey Fletcher also did very well. He was able to author other papers on this topic, on the experiment, and received his PhD. And then he went on to do seminal work in stereo sound, acoustics, atomic physics, and many other topics, and he worked at Bell Laboratories a long time. He actually recorded albums with Leopold Stokowski. And again, you can look up who Leopold is. An article was published in Physics Today in 1982. Harvey Fletcher had written it and said that he only wanted it published after his death. In the article, he described his relationship with Millikan and stated that he was very happy with the way that everything turned out, and he was very grateful to Millikan. And if you're interested in reading it, here's the reference, Physics Today from June of 1982.